Welcome. In this video, we're going to take a look at the fundamental theorem of calculus. And if you remember from class, it's sort of the really big, important theorem that allows you to find the area under a curve. So if you're given a function f of x and you want to find the area underneath it, you need to find an antiderivative of the function, and then you can just plug in the endpoints or the limits of the integration. And once you find the difference between those, that apparently is equal to the area. Now, there's a little bit of a mystery behind that. We never actually really showed why that is, and that's the purpose of this video. So we'll start off by just reviewing what we've got so far from class. We've said that the definite integral from a to b of the function f of x with respect to x gives you the area. And that apparently is just done by finding an antiderivative of the function. We'll call that capital F. And then finding the difference of that antiderivative between a and b. All right, so let's just see how that actually holds up. We'll call this a proof, although it is kind of a sort of brief sketch of a proof. What we're going to do is, instead of trying to show that something is an antiderivative, we'll show that the derivative of area, or the rate of change of area, would actually be the function f. So let's start off with that piece of things. Imagine that we want to find the rate at which area is increasing. You'll do that by taking your function, starting at point A here, and trying to shade it on your way to point B. Now, it makes sense to shade it from left to right as x is increasing, and see what happens to the area. We'll start shading, shade a bit further, and let's suppose we haven't quite shaded all the way. We've shaded up to some value, call that value t. So let's just define that. That area, let's call it a. Better off, let's call it a of t. It's actually a variable area depending on where you stopped. I may have stopped at a different place than you did, so let's just call our general area a of t, where t could be as far as you like. That's the area from a to t, or as an interval from a up to t. Now, to see how that's changing, let's shade a bit further. Imagine that you shaded a bit farther than wherever you left off last, and that would be t plus a bit more. Call that h. We'll still use a. This time, instead of stopping at t, you're going to stop at t plus h. Now that's the total area from a to t plus h, or as an interval from a to t plus h. And let's say that h is very small. And it's still important to know that we haven't quite reached b yet. That just kind of helps you to be able to visualize it. We're having a problem getting to b. We want to just know how far we've gotten and how quickly it's changing from here on out. Well, take a look at that green area. If it's pretty small, like how I've drawn it, the difference between a of t and a of t plus h, that's green area, we could write as a t plus h, the total area up to t plus h, minus the area up to t, is approximately a rectangle. Well, area of a rectangle then. Now, what is the width and height of that rectangle? The width of that, you could see, since we're going from t to t plus h, would be a width equal to the distance we've traveled, which is h. And the height of that, well, it's not exactly a rectangle, you have to remember, but it's not really dipping too much lower than it started. It's not going much higher than it started. So what if we just use the point on the curve where x is equal to t, in which case the height of this rectangle is approximately f at the value t. Well, you multiply those two things together. The difference in area of the total shaded area minus the shaded area in red gives you the shaded area in green, which is approximately equal to a width h times the height f of t. Now let's manipulate that a little bit. Divide both sides by h, which is some arbitrary distance along the x-axis. And we'll say that that is approximately equal to the height of the function at f of t. Now, it's not exactly a rectangle, as you can tell. It doesn't have a flat top. But if we were to make h get really, really small, then there really couldn't be that much of a change from the height at t to the height at t plus h. It would be more or less a perfect rectangle. And that's where we let h get very, very small, and we say that the limit as h approaches 0 of a t plus h minus a at t over h should be equal to f of t, the exact height, as long as h is exceptionally small. We let it get infinitely small. Now, if you stop there for a second, I'm hoping that looks pretty familiar. You've seen that before, where you have a difference of two things with h's divided by h as h goes to 0. That is the rate of change of h over a very small value h, and we call that the derivative. This says that the derivative of area, the rate at which area is increasing at any point in time, is equal to the height at that point in time. Now that is kind of our big first step. We found that the derivative of our area at point t is exactly equal to the function. So that means then that the area, total area from point A up to t, is an antiderivative of the function. So we could actually change this into a statement that says the total area is equal to an antiderivative of the function. Now, here's where we have our plus c. Because when we're talking about a general antiderivative, we could have any kind of constant added on top of that. And that is the first half of the fundamental theorem of calculus. This would be the area on the interval from a to t. We could write it one of two ways. We could just say a to t or a comma t. Now, a couple special cases will allow us to figure out the constant and the total area. So let's start off with one particular value of t. Let's let t equal a. Now this would be graphically kind of a silly case where we've got our function. We're starting shading in the area at a. We're trying to work our way to b here, and we're saying that how far have we shaded? Well, we've shaded nowhere. We're still shading this line. We actually haven't left the starting line. Well, what area is that? The area has to be 0 because I haven't even gotten started yet. So in this case, if t is equal to a, this area is equal to 0. Total area up to point A equals 0. Now, using what we found so far, this means that f of a plus c has to equal 0. Well, that tells you c has to be equal to negative fa. Now we can make that little substitution. We're going to take this negative f of a, we can plug that in here for c. So we can update this. Now we've got that the area up to t is equal to f of t minus fa, where f is an antiderivative. So if we want the total area, we just have to shade all the way up to b. Let t equal b now. Graphically, that's the whole thing we're looking for. We've got our increasingly gross looking function every time I try to draw it here. Going from A, we finally get the shade from left to right, past our previous value of t, going even further past our value of t plus h, going all the way and finally shading the whole thing. Well, in this case, the area of the whole thing is equal to what we're trying to solve for here, the actual definite integral from a to b of our function. According to what we've got here, ft minus fa, that integral must be equal to fb minus fa. And that's what we were trying to show all along, that all you need is an antiderivative. But now you can kind of see how it works both ways. The rate of change of area is actually equal to the height of the function at any point in time. So then the total area has to be the integral, the antiderivative of the. Right. Well, I hope that kind of helps kind of clear up what the fundamental theorem of calculus is all about.